Welcome to Emerging Technology Horizons. I'm Mark Lewis. I'm the Executive Director of NDIA's Emerging Technologies Institute. And with me on today's episode is Jim Faist, who's Vice President, Chief Technology Officer for Technology, Innovation, and Labs at CACI International, leading the development of advanced 5G, artificial intelligence, electronic warfare, EW, cyber, and communication technologies in support of future intelligence, surveillance, reconnaissance capabilities for both the intelligence community as well as for the Department of Defense. Before that, though, I had the honor and the privilege and the daily pleasure of working with Jim when he was DDR&E, Director of Defense Research and Engineering for Advanced Capabilities. I was DDR&E for modernization, so we worked not only on a daily basis but on an hourly basis, and it was one of my great pleasures of being in the Pentagon and most recent position. Among his many areas of expertise, Jim is a longtime industry figure. He's an engineer with a very strong background in sensors, weapons, electronic warfare, and those were areas that he focused on in the Pentagon. But also under Jim, the Pentagon focused heavily on the whole issue of digital engineering and digital transformation as a means to enhance the way we research, design, procure systems, the way we sustain systems, but also to reduce schedule and cost for future weapons developments. And that's going to be the topic of our primary topic of discussion on today's episode. So first of all, Jim, welcome. Thank you so much for joining us in this episode.
Thanks, Mark. It's nice to work with you again. Those were amazing years in the Pentagon, really shaping the national defense strategy and really all the great work we did in many areas so that we see today. So I think it's great that we're all still participating in this endeavor, which is how do we provide for national security going forward? It's really a critical issue for the country. So I appreciate ETI really bringing me in and publishing my article about digital engineering. So really appreciate the time and effort you guys are doing today.
Yeah, no, my pleasure, and likewise, the work you did in the building was amazing. The amount that you got done in the building, and it was a relatively short period of time that we were all there, but we sure seemed to get a lot done and set the tone. Set the department on a really important path in a number of key areas. So let me start out by asking, there seems to be a lot of confusion about what digital engineering actually is. I'll have people stop me and say, is it just fancy CAD CAM? Is it something new and different? Is it, well, frankly, the latest buzzword, or is it something that's really significant, really transformational? I'm a true believer. I do think it is something transformational. But could you start out by tell the audience what is digital engineering and what is the impact that it can have?
Yeah, it's easy to miss what the value is. So way back when we started as an electrical engineer. Digital engineers design analog circuits, digital circuits that we see in processor cards and stuff like that. What's changed over the years is as you get better digital representations of systems in CAD systems, but also in just being able to look at data coming out of systems, the data part drives the architecture more than it ever did. It used to be way back when you would design an analog part of the system, you would do RF part of the system, you'd bring them together and you figure out, okay, how does this system really work? Digital engineering puts everything in a digital domain at different levels within the design that if you use it the right way, gives you better products, it short circuits the design time, but also improves the quality and rework you have to do in systems. So that's the big difference in digital engineering. There's many examples of it, but it gets into the complexity of the system that you're doing. So when people talk about is it CAD systems, well, as a CAD system you might use to design an IC, and then that goes into a CAD system that designs a board that you put an IC on, and then you put it into a subsystem. It gets a little more fractured because you have more mechanical models and you have digital models and stuff like that. And then the data that comes out of that, how do you use that data? So when you hear about digital engineering, it takes different forms. So if you're looking on the system engineering side, people remember back to, okay, how do you do requirements definition on system development? And they built tools around that people would call almost auditing tools. You think of doors or some rational or other way to collect requirements. And the purpose of those systems is to build databases of requirements so that you don't lose traceability throughout the design process as you went. And those work. Did it shorten the design time? A A little bit, but the end products you see, you wouldn't say that, gee, everything is being built faster nowadays than it was 10 or 20 years ago, right? It's probably done with fewer people when you look at numbers of teams working on things because of the automation, but the end products are probably about the same pace. What's changing now, and I didn't talk in the paper, is MBSE, model-based system engineering, which is then taking those system engineering tools and attempting to integrate them all together throughout a system. So if you have a really complex system, like at CACI, we're doing a lot in shipbuilding. You might have a boiler, or not a boiler, you might have an engine within the ship, and you may have sensors on the ship and weapon systems. Each one has a different design cycle. MBSE attempts to bring the system construct into the same structural format. So in that case, the Navy system engineers can work with industry system engineers to make good design decisions. So when you get to a system requirements review, you have traceability that's easier throughout a system. So the engine will fit in the hull, and then the sensor will fit on the ship, et cetera, and that flows through the design process. So it gives you better accountability when you do it. Now the challenges are, as you know, so the problem MBSE doesn't solve is, say you're designing a sensor on a ship. As you know, if you're building an RF system on a ship and say it's a big antenna, the architects and the people that do the high-end signal processing analysis, the MATLAB, MATCAD type design work, the algorithm work to figure out how that antenna is going to work or interfere on a ship. MBSE takes the output of that, but it doesn't usually trace the physics that go into that part of it. So that is the area that you have to look at. How do you maintain those type of physics-based models when the scientists and the high-end scientists and engineers that created that aren't on the project anymore? How do you translate it so that if you change a mast on the ship, does it give you antenna interference on the ship that, hey, it's not going to work as well? So that's the dilemma we got a little bit, I think, on system development. And then if you look at how, like we were doing the Pentagon, how you might do a campaign model, okay, now you have, in your case, Mark, you're a hypersonic expert. So you have a model of the hypersonic weapon, and you're using that in the simulation. How accurate is that model? You'd want the digital artifacts both on the data that are going out of the missile into a fire control system or into some other use with the service systems, but also, what does the sensor really do? It's it's a very complex problem, and that part of the modeling is the hard part, right? When you talk about model-based system engineering, because as you know, we could build a weapon system to all the requirements, and you put it in the field and you test it, and you find out, gee, it doesn't really do what needs to be done, right? So you have to be a little careful about it.
Yeah, I guess, is it correct to say, draw the analogy, I know the way we use wind tunnels, for example, has changed over the years. Whereas it used to be we do hundreds of cycles in a wind tunnel, now we might do a handful and we fill in the gaps with modeling, simulation. So we're not necessarily, we're in some cases reducing the workload, reducing the manpower. Also making it easier for collaboration, it's so much easier to exchange information, exchange data.
Yeah, you have to have the network layer, and a network layer has to be, the hard part too, at different classification levels within the network. You have to connect the right people that they can operate quickly. As we know, the boundaries with different classifications is an impediment. And it is an impediment to digital engineering because once you get out the small team, you're losing the connectivity with the engineering community, right? So that's certainly part of it. It's kind of like the same thing, back when I started out, I worked on most of the RCS ranges in the country, everything from the F-117. I think my last one was the F-22. And it was kind of the same thing as the wind tunnels, right? Initially, everything had to go through a chamber test. Now, a lot of modeling does a lot of that for you. But then when you get the whole system together, it's just too complex that, you're not going to not get away from doing RCS measurements, just like with the wind tunnel. I'm sure it's the same thing.
I once had an Air Force engineer tell me that he worked on the F-15, and he said, they knew the mass of every single piece of the F-15 down to every last bolt, every last washer, and they could tell you exactly what the mass of the airplane should be. And when they all assembled it all, it was always slightly different, and always higher. Oh no, Of course, always higher. So.
Yeah. So I did see one good example recently where an airplane, a vehicle that was built entirely with digital engineering and a lot of investment, because it takes a lot of investment on the developer in those tools and models, the network connectivity, You have to have discipline how you orchestrate the index on how you use that. And it looked like to me they developed that in about half the time with a tenth of people. And in that case, way back when they built airplanes, they would build a physical model and they would see how it fits to the next part of the aircraft. And what they're finding is, at least that's on the mechanical aerospace side, that's more your background, is that those models are really good now and you can integrate things a little quicker. So we should be able to build prototype airframes and stuff like that a lot quicker than we have done in the past. That's a good example of maturity in the models, right?
Yeah.
Hypersonic systems being developmental still, we don't have a baseline. They're going to be a lot less mature until you get through the basic physics of getting those systems to work. Right? And then how do you maintain the data on the hypersonic weapons you're developing that gets connectivity to the production part of hypersonics is going to be a real challenge.
No, absolutely. I'm thinking in terms of, again, shipbuilding as an example, where a piece is built here, a piece is built there. They bring them together. They fit together exquisitely, like every last nut, bolt, pipe, you name it, all due to digital engineering. So that leads to the question: what's our current state right now? Where are we in terms of integrating digital engineering into the way the department does business, and what are the current limitations?
I think, well, first it gets into how we acquire systems, right? If you ask any developer today, are digital engineering techniques, processes, and outcomes substantiated in RFPs, requests for proposals that industry receives to build systems, they will uniformly say no, right? Because, and you've seen it, Mark, you've been there, how requirements are developed to produce a system is really not conducive for that. You can see it in like the 804 prototyping things because they're a lot looser, but when you get into the traditional MDAP procurements and how you might build something, it needs to be fixed there. Because it has to be something that industry sees when you're competing a missile or competing a ship or a helicopter, that MBSE or digital engineering, proving it out in your proposal gives you a discriminator that lets you win the job, right? Until it's substantiated in that and scored that way, industry will do it as they see they have to. If they see a benefit, just a natural benefit that, hey, I can cut down, engineering levels here a little bit to get my bid more competitive. I think I can feel less risk adverse on the production schedule I propose with this. Those are all good things, but does it really translate to you winning the job or not? Right? That's really the issue. So we got to fix that, I think, is probably the big thing. The next big thing is, and this, the fact that the engineering levels in the government side were so depleted at the end of the Cold War, like a lot of things, because the shift was not on modernization, that the whole DoD engineering workforce, the government side, needs to be rebuilt. And part of that are professionals that really live and breathe digital engineering. They understand it. They get background in that. They have the competence to go ahead and do that. So that gets into that other part I had in the paper, which was a lot of the conflict of interest of people moving between the civil sector and the government sector are for good reasons, right? It's program management types and people that have the business control over things. But engineers really, and the practice of engineering, as you know, is the same whether you're doing commercial development or government development. And we need to leverage the ability to move some of the really good industry people that want to serve, they're really good engineers in the federal government for defined periods. I mean, DARPA does a good job like that on the PM side of doing technology development, but the people that are actually practicing engineering, doing the work, running the models on the government side, we'd be able to move the government side a lot quicker on this.
Yeah, and of course, the department already has ways to do that. The Highly Qualified Expert Program, HQEs, the IPA, the Intergovernmental Personnel Act. My first job in the building was as a university professor, but I was an IPA to the Air Force, right? So we've got those capabilities. Yeah. It just seems like we weren't using them to the extent that they were that we could.
And it's so hard to recruit people, right? You've seen it. It's very hard to get people. Just the process is so slow to bring them in the government. So I think that's one thing. The other thing, when we did the digital engineering policy, I brought in some people from industry, some retired people from industry that did a really good job. But I think what we need to do on the discipline side, when you look at the OSD policy, is we need to create an index structure to digital engineering to tighten it up a little bit. I mean, you have that on when you talk about WBS structure, work breakdown structures on programs. We need something similar like that on digital engineering, so you have common indexes. So, like, say, back to the ship example, if you have a model for a ship engine here, it's used commonly in other places within digital engineering, so that practitioners of that technology and engineering have easy access to other work being done across the
Yeah.
DoD, right, on the government side. And we didn't fix that on on the last version. That's something that needs to be handled as well. And then the whole thing of mission engineering, which really gets into, as you remember, we put out the mission
Hmm.
engineering guide,
Hmm.
which was a good thing, which is really architectural part of it. That's the architectural of system engineering that we call mission engineering. That also needs to have more digital engineering output structure for the data that comes out of it that aligns with an index. So, if you're
Yeah.
designing
I like this
go
example,
back to
by
your
the way.
hypersonic weapons,
Yeah. Yeah.
we have a lot of hypersonic programs, right? They're developing different aspects of that. Are we capturing everything in the same framework, the same index that's available first to the government, but then also industry as they compete for that? Because when you start doing that, as you know, you get better
Yeah.
technical answers at the end, right? And you don't repeat the
Yes,
same
that's right. That's
problems
right.
over
That's
and
right.
over again.
Absolutely.
So,
Absolutely. So
yeah.
let's talk about some opportunities to accelerate. In your paper, you talked about accelerating DoD modernization through digital engineering. Um, could you step us through some of those? You talked about providing continuous evaluation of a system's ability to address a changing threat or mission. What does that involve?
So that's a good question. So, as you know, and I was new coming into the government, like you. I spent all my
Hmm.
career in industry, so I was familiar with the ITRA process, which was independent technical risk assessments that were
Hmm.
being
Hmm.
done. And then that's kind of the same thing on development testing, operational testing, all three of those elements, whether it's during the design, the testing, or whatever, all just part of system engineering, right? Those need to be integrated, right? And really good quality system engineering is integration of functions to achieve the mission. The way they're broken out in the government, as you know, when you get the stovepipes, it's not very effective. And most all the valuable independent analysis is on the front end. If you talk about the design cycle, it's the SRR and the PDR are the most important things. CDR means, okay, now I'm ready to actually build it, which is closing out the requirements to the hardware and software architecture that you've decided. Um, the more you put into the front end, the better outcomes you're going to have. But one thing OSD was not doing is this. The old JSIDS process and everything. It's basically and this was a General Hyten comment. By the time you get some through the JSIDS process, it takes years, and then you get it out there, and the threat has already moved 2 years beyond where we are. So the JSIDS process really doesn't work. You have to put the ability to continuously evaluate what you're developing against the threat. Just like it was during the World Wars, we're always improving and evaluating systems based on what the threat was doing to save lives and persevere. That is not there now. That needs to happen within OSD leadership and then the service leadership. And it's engineering governance driven that says, okay, we're going to have to pick your system, the hypersonic weapon. We're developing against these parameters. How are those going to change over the next few years? Is the design flexible? That part of engineering is what's missing. And if you're not doing that, the problem, where you get slow is, what happens is you get to the testing part, and then suddenly you see, gee, this isn't going to work that well against the threat systems because of many reasons, right? Could be many, many reasons why it's not working. Think of what ends up happening. You end up going back to redesign it again, and then suddenly a 2-3 year development program is 6 to 9 years, right? And by the time you field it, you say, gee, it's not as effective. So we should know, Congress should know, everybody should know at any given day how effective this system is going to be when it's fielded against the threat. If the threat changes, either you cancel or modify the program to go forward.
And of course, I'm thinking also of, we have examples now of weapon systems that have been used for decades. The threat has changed dramatically over the course of over the lifetime of the system. The B-52 bombers, the youngest B-52 bomber in the fleet is actually older than I am.
Me
Yeah,
too.
it's
Yeah.
and
It's amazing, isn't
yeah,
it?
we
Yeah.
never anticipated how we would be using it, and having a digital tool available that could account for that changing threat would obviously
Yeah,
be
B 52 would be an example. It's a platform that carries
yeah.
things, right? So that's why it's there. It's a great resource. The airframes, because of the Cold War, don't have high hours on them. They're good for a long time, and they can carry enormous stuff and then launch it. So we don't have anything quite like that at this point.
Right, right.
So, but you just repurpose it, and then the weapons that go on there are the ones that matter based on the threat of what you're doing. And the China architecture, and you saw it too. The China architecture is so dramatically different. You just have to, whether you call it the China filter or whatever, it just changes the paradigm on most systems that we have out there, how you operate. And the assumptions that we had prior to it's back to the Cold War, right? The assumptions of air superiority aren't there, and how you're going to really operate effectively drives a lot of this stuff. But to go faster, that's what you have to do. And then you have to have more continuous engineering governance within the department. I mean, I didn't realize a political appointee type position. I never really heard of it before I went into government. But just as we have appoint judges for terms, we have other people that are nationally important, engineering leadership needs to be longer term than a political appointee. It should be a term position. We have defense science boards that do a great job looking at technology, and we always seem to do really good on that end of it. But as we've heard many times on the engineering side, we don't perform that well because there's no structured governance and there's not continuity in the people that are running engineering that are accountable to do it. Engineers want good engineering leadership. They want consistent things that they can do good work against. And as I said earlier, it's no different doing engineering work for DoD than the commercial world. It's just the commercial world is driven by the profit loss margin that really drives you to do good work or you can't compete. Defense isn't that way. It's the threat driving engineering. So we need engineers that are tied with the threat, that are going to be there for a reasonable amount of time. They don't want to be there forever, but you want to be there for a good amount of time, 4 to 6 years to do that. And they need accountability to the people, the Congress and American public to deliver defense capability.
Interesting point. It was frequently pointed out to me that there are certain positions in the government, FBI director, for example, that's a long-term appointment that's deliberately intended not to, although it's politically appointed, to provide continuity. And I agree. I mean, we certainly saw a revolving door when we were in the building.
Yeah. Yeah, Federal Reserve Chairman is 6 years. I mean, how many billions a year do we spend on engineering in the Defense Department? And you could say that about other government agencies like NASA and others, but a consistent engineering leadership over an appointed time would be a better answer than what we have.
Yeah, absolutely.
And you could probably say the same thing on acquisition leadership too, not just engineering. But today we're talking engineering. I think that would be the same.
Exactly. So if I can switch gears a little bit, one of the points that you made in the paper, you did a call for a defense engineering board, and I'm wondering if you could tell me a little bit about your thoughts about that. What would such a board do? How would it function?
Yeah, so I think it's a board that you would want to split between engineers from industry and government that have peer review, just like we do in engineering circles, to make sure you get the right talent for the mission. They're appointed for positions. They have a chair that chairs it. And I think they really are, you can't really have a matrix like probably the better development companies have matrix engineering organizations, but you need a path that the engineering parts of the services have a path that they can communicate engineering up through a different chain. The part of it is in really great development efforts is a partnership between program management and engineering, and they're usually two different departments, right? And you have to work out something that works for both parties. You don't have that in DoD. It's basically an acquisition arm with engineering support. So a defense engineering board is the start to give engineering authorities within the services. And when I did put the paper out, I can tell you I got many chief engineers across the services give me a thumbs up that they need a path that says that this is the right engineering approach on these systems, and also fix the policy parts too, the governance and how we do engineering, improve independent oversight, because in any company, program manager has different drivers what they're trying to do, which is cost, schedule, and showing deliverables. Engineering cares about the technical baseline and is it going to work, and risk, right? And both need to be communicated better. I think some of the communication issues you have, if it's just acquisitions, right, it gets too politicized. And I think you need a little less of that. It needs to be a little more of a balance balanced, objective look on every program to see, okay, this is really working
Mhm.
well, and lots of
Yeah.
them do. Lots of really good programs are producing good stuff. We're taking high risk, like hypersonic. We're taking high risk. We're trying to move quicker. We don't want to get burdened down with programmatics until we really have something that works, right? And once you have something that works, then the balance tips a little bit more to acquisition to get the system in production, and then sustainment is the other arm. And each parts of those, there's engineers throughout, but as you know, the part that's broken the most is on the development of the new systems, right? Get them done, get the designs to where they're mature, they're executable, they're reliable, then get them into transition to production. If you try to rush them into production, you have something that doesn't work and you have to rework it, et cetera, and you go a long list of programs that don't do that. So the only way you're going to fix that is more engineering authority and more engineering governance.
So we're almost out of time, but before we go, I've often stolen a quote from you. People talk about the valley of death, and you once said to me, "It's not a valley of death; it's actually a mountain of death." And you pointed to
Yeah.
the funding profiles, and also I thought had a really nice perspective on that. That actually you want to filter. You don't want not every program is going to make it through to from the laboratory to a program of record, and that's actually a healthy thing because it keeps fresh ideas coming. Am I capturing that right or?
Yeah, I mean, it's always nice to have developed technologies. DARPA's great at that, right? They'll develop some really cool stuff and they take it far enough to solve the hard problem. And then people say, well, DARPA doesn't transition. Well, it's really not their job, but they developed something really cool. And then the engineering community say, okay, I want to accelerate it to the next part. So kind of we did that on the sci-fi program, right? Okay, we're trying to accelerate it to cut the timeline to finish the engineering of the system, right? To get it to a point that now the services can pick it up and get closer to acquisition and production. That's the valley of death. So all you need is just good engineers and the mission people. So if you understand the mission and the threat, where's the priorities of what you're trying to build, you could look at many other programs like NGAT and other things the department's wrestling with and say, okay, this is when I'll pull these harder and pull them into reproducible prototypes that are closer to production. And that's where digital engineering would come in, because if you look at you're building a prototype aircraft and you say, gee, the models are really good that we can short circuit development cycle by a couple of years if we go with this particular vendor's approach, that's a good thing, right? And then suddenly we can produce more aircraft quicker and stuff like that. So yeah, it is a mountain, but I think you just need smart engineers to find the path up the mountain for the technology that you're trying to advance in the system.
Absolutely,
right?
absolutely. That's a really good point on which to conclude our conversation, because I agree with you completely. Hey, Jim, thank you so much for joining me for this episode. As always, a pleasure. I said every day I got to work with you in the building, it was a privilege, and it's a privilege to be able to continue working with you on a variety of projects. So thanks again for joining us in this podcast.
Thanks, Mark. Thanks to ATI.